In lesson 1, we had talked about similar polygons, and we're going to continue that discussion today in lesson 3. But today we're going to focus specifically on triangles. Now we know if figures are similar, their corresponding angles are congruent and their corresponding side lengths are proportional. And we had to check all of that in order to determine if they were similar. Well, for triangles, there are actually some shortcuts that you can use to prove your triangle similar. So you don't have to check all 3 sets of corresponding angles and all 3 sets of corresponding sides. The first shortcut that I'm going to introduce you to is called the angle-angle shortcut. It's angle-angle similarity, so shorthanded AA. It says if two angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. If you take a look at this diagram here, we know A is congruent to F. We know B is congruent to G. Why is that enough information to prove? Well, by the third angle theorem, we for sure would know that angle C would be congruent to angle H. And when I have my angles congruent in my triangles, my sides are going to end up as proportional. And so if we needed to write our similarity statement, I'll just remind you that we need to make sure that our letters are in corresponding order. If I say A, B, C, I need to then say similar to F, G, H. Sometimes the angle-angle similarity shortcut, instead of just saying AA, you might see it written like this, AA with the similarity sign, so that you know you're not proving a congruence shortcut. The second one is the side-side-side similarity shortcut. And the side-side-side similarity shortcut says if the corresponding side lengths of 2 triangles are proportional, then the triangles are similar. So, taking a look at our diagram, there are 2 triangles. I'm going to go ahead and put in some numbers here. It may not be completely drawn to scale. But do you agree this is showing, I have all 3 sides for each triangle. I don't know anything about the angle measures. But when I look at my corresponding sides, 9 to 3, 12 to 4, 18 to 6, all of those would have the same ratio, right? My big triangle to my small triangle, I can say, well, my ratio would be 3 to 1. So knowing that all of those ratios are equal, I can say that this would have the side-side-side similarity shortcut. It would prove my triangles similar. There's one more, and that last similarity shortcut is side-angle-side similarity, so SAS. Again, that is also a congruence shortcut, and so when you see that shorthanded, a lot of times people will put the similarity sign behind it so that we know we're not proving congruent. Okay, the SAS similarity shortcut says if the lengths of the 2 sides of one triangle are proportional to the lengths of 2 sides of another triangle, and the included angles are congruent, then your triangles are similar. So you're checking your 2 sides, proportional, and your included angle congruent. So right now, in my diagram, I see angle S and angle Y are congruent. To show SAS similarity, I'm going to have to put some numbers in here. We know the included angle means in between. And as I look, small triangle to big triangle, and I compare 3 to 6, 2 to 4, we see that those have the same ratio. I have 2 sides proportional, included angle congruent. If I needed to write my ratio, well, it would be a 1 to 2 ratio. So they're going to give you some diagrams today, and they're going to ask you to determine if you can prove your triangles to be similar. And sometimes that won't show you a shortcut. And so we're going to have to say at that point that we cannot determine it. So in example A, we're going to see if we can determine it by one of the shortcuts. And if so, or if possible, we're going to also give the ratio. Now, as we look at picture number 1, we see my triangles. As given, it does not show angle, angle. I should, though, calculate my missing angle, 46 degrees here, and over here, this one would have to be 43 degrees. So, you know what? No, these triangles are not going to be similar. If I had to explain, I might just say that my angles are not congruent. Picture number 2. Picture 2 is interesting. There really isn't anything marked. But I do see these arrows here show me I have some parallel lines. And we know that right in the middle, we can mark some vertical angles. So I have my pair of angles marked at vertex S. My parallel lines, would you agree, I see some alternate interior angles. So angle R would actually be alternate interior with angle W. That right there shows the angle-angle similarity. Now it is true that I would also have this angle at X alternate interior with my angle of T, or by the third angle theorem. So I'm going to say, yes, these are similar, and this shows the angle-angle similarity shortcut. Now, because I don't have any side lengths given, I don't know specifically what the ratio is. I only know that my triangles are similar. And the last one in picture 3, well, we have some side lengths given. Let's go ahead and compare. Now, in my small triangle, my smallest side here has a length of 5. Sometimes kids are confused as to which one that would correspond with. Well, my smallest side here has to correspond with my smallest side in triangle RST, which would be 12.5. So this side corresponding QR to TR. And I like to just go ahead. It appears that we may be able to use side, 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 but we have to check each ratio. So my next side length, 6, is going to correspond to 15, and 8 is going to correspond to 20. And we want to see if all of these have the same ratio. Now, I can pretty quickly reduce these, knowing that 3 goes into both of them, and 4 goes into both of these. Now, the decimal you might have a little bit of trouble reducing. You can certainly divide that on your calculator. Or if I swing this decimal over, this would really look as 50 over 125. In the end, you will find it does come out as 2 over 5. And so, yes, I'm going to say that I can use the side, side, side similarity shortcut. My ratio, 2 to 5, or 5 to 2. But you know what? There is one other thing in this diagram. We could have marked some vertical angles. And so not only could we use side, 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 but I could have used SAS, side angle side, because that vertical angle is included. Okay, let's take a look at some examples on the back. As we did in lesson 1, we can use our similar figures to solve for some missing information. And in these examples, we are given the fact that these triangles are similar. They want us to find each length or value for the variable. As I look at picture number 1, I can see that both of these triangles have the 90-degree angle, and they actually have that shared angle at angle A. So they would have angle-angle similarity. How would I set up to solve for my value for X? Well, I picked this question because many times kids will want to say, well, X corresponds to 5, and 9 corresponds to 3. But that's not right. If we are going to use the triangles, do you agree that the bigger triangle, the side length AC, is not 3, but it is 9 plus 3, or it is a length of 12. So if I'm going to set up my corresponding sides to check my ratio is not 9 to 3, my ratio is 9 to 12. So 9 over 12 should be the same ratio as 5 over x. And I could reduce this and reason through what x should be, or I could go ahead and use my cross products. Divide by 9. Now we are going to find that x comes out as 6.6 repeating. So I'll remind you, I would want you to write your answer with the repeating sign, or hopefully you know 0.6 repeating is 2/3. So side CD must be 6 2/3. And it's always a good idea just to kind of double check to see if your answer makes sense. In picture number 2, we are given that RST is similar to BCD. Find the value for x. Sometimes it can be confusing as to which sides correspond. And so if I'm not sure which side corresponds with ST, I'm going to go up here and check the order of the letters. ST corresponds to CD, so my side 70 here is going to correspond to my side 50. So right now, well, I know my ratio is 7 to 5. And that should be the same ratio as my side SR to my side BC. Now, I cross my zeros off just so that I'm going to work with smaller numbers, but I'm still going to use my cross product. So I'm going to take 7 times 60 and 5 times the quantity 11x minus 4. I'll remind you that this is a question where we would need to distribute. It is times the quantity. And so we're going to say 55x minus 20. Add 20 to both sides. And divide. We would find out x is 8. So up here, okay. Question 3. In question number 3, first of all, you kind of want to picture your two triangles. I have given that angle R and angle T are congruent, and again, these have the shared angle at P. So I have a smaller triangle and I have a bigger triangle. I know that my side 4 corresponds to x plus 5. But my other side, my ratio is not 3 to x, because the whole side for that bigger triangle is P to s. How would we express that? Yes, we have to combine these, or add them together, I should say. So that was going to be a side length of 3x. So if we're going to set up and solve, 4 corresponds to x plus 5. This ratio should equal 3 to 3 plus x. And again, I'm going to use my cross products. I need to make sure that I distribute. I'll set this up 4 times the quantity, 3 plus x, should be equal to 3 times the quantity, x plus 5. If we subtract 3x from both sides, I'm going to end up with 12 plus x equal to 15. Subtract 12. And we find out x equals 3. Which would make sense. It seems reasonable that this would have a side length of 6 and that this would have a side length of 8. Okay, let's look at one last example. Example 4 is asking us to explain why triangles Now there's actually, or are congruent, there's actually three triangles here. I have to determine which two I'm trying to prove similar. ABD is the smallest triangle. ACB is the larger triangle. So I'm using the smallest and the largest. I'm not using this medium triangle, BDC. Well, this one can be a little bit difficult to see, but I notice up here, you know what? These triangles both share an angle. They share angle A. And this side length here of 4 and this of 12, well, that would mean this side of AC would have to be 16. We're actually looking for AB, so I'm going to put an X there. This can be difficult to set the ratio up because our triangle, the one inside the other is also rotated. So I'm actually going to sketch them separately and show you what that would look like. If I had my large triangle, ABC, this is kind of what I'm looking at for my triangle ABC. Now I'm going to take my triangle ABD and I'm going to rotate it and I'm going to reflect it so that they're in the same orientation. And so my longest side of my small triangle is actually AB. And D would be at the top. Angle A and this angle B are marked congruent. AD has a length of 4. AB is what we are looking for. Once I have separated them and drew them separate in the same orientation, I have a much easier time setting up my ratio. I know that X, this side here, is going to correspond to 4. And my side 16, my long side here, is actually going to correspond to X. Well, what are we going to get if we solve here? I'm still going to take a look at my cross products, and we'll actually find that we see x squared is going to be equal to 64. Well, we know we would take the square root of both sides, and we had talked last time that, you know what, x could really be a positive or negative 8. But this is an example where we looked to, or double check our values, and x could not be a negative side length. So in the end, we're going to say that x is going to have to be 8. We would not use the negative root, and therefore my side length of AB would have a length of 8 units. Okay, if you have further questions on similar triangles or the shortcuts, please step in and see me.